Hi, welcome to you. Thank you for taking the time today and joining me for my presentation. My name is Thomas Verheyde. I'm a PhD candidate at TESA in Toulouse. Today, I will share with you my latest research results on smartphone collaborative positioning in an urban environment. The outline of this presentation is structured as follows. This year, ION conference being virtual, I decided to put in place time codes for each chapters and subchapters. This will allow you to come back anytime to this presentation, finding the chapter of your interest. Now, let's jump into the introduction. To start with, a little bit of context. I would like to introduce what I like to call the virtuous circle of Android GNSS raw measurements. At the beginning, we find the Google API allowing for the first time in May 2016 users and the scientific community to have access to GNSS raw data measurements. After this was put in place, chipset manufacturers took advantage of this new API to develop enhanced GNSS chipsets for smartphones. It then created new functionalities on recent Android phones before being tested by users around the world and asking for more control over the embedded system by implementing the original Google API. And then the loop goes on. This virtuous circle created a huge enthusiasm for Android GNSS raw data measurement, creating more advanced smartphone hardware and achieving important milestones. This study has been motivated by my current research project about collaborative positioning in urban areas for low-cost mobile. We're focusing our research on smartphone GNSS functionality. Why is that? Because we envision a smartphone network as the biggest GNSS network on the planet. We would like to take advantage of this volume of potential GNSS receiver for addressing current urban environment constraints linked with satellite positioning. And now, with this research, we are on the second bullet point about the assessment of collaborative methods. Copying and understanding the wide variety of Android smartphones could be an impediment to the creation of innovative algorithms. Therefore, in this presentation, we will tackle those problems by first developing a methodology of smartphone positioning performances for nominal and urban conditions. Then we will be evaluating existing collaborative techniques and we will see how we can apply their algorithm in the smartphone domain. And now let's move on to our assessment methodology. In order to characterize our smartphone for nominal conditions was to focus on four main parameters, such as the phase jitter, code jitter, Doppler jitter, and finally the clock drift. At the end, we will be comparing the smartphone error levels to the COTS GNSS receivers. The two pictures on the right here represent our testing conditions for open sky environment. Our results will be displayed in this kind of table. So on the right side, we will find the smartphone that has been tested during our analysis. And on the left side, we will find the GNSS receiver and smartphone that has been tested during a study made by Letola and Orr. Now, if you find any additional lines present on this table, such as for the Honor View 20 and the Xiaomi Mi 8, they are representing the second or third similar phone used for the project. As an example, here we are showing the estimated DLL jitter error obtained and how do they compare against the COTS GNSS receivers. Here we can notice that the estimated DLL error on smartphone is similar to what we can find on the U-Blocks receiver. It's especially the case for the Honor View 20 smartphones and the Xiaomi Mi 9, for example. Then we can also see that some smartphones behave differently, but still are in the same order of magnitude. And on the top left, we can see the model that we used for modelizing the DLL jitter, and we used a Gaussian distribution. Now we will switch to the urban environment studies that we made. In order to do so, I will present to you an experiment protocol that we use for this study. We used 7 recent smartphones. They represent the diversity of Android that we can expect to find in today's city centers. Moreover, they use different chipsets from the 3 main chipset manufacturers. They are all operating Android 10 OS and all have multi-frequency and multi-constellation GNSS capabilities, except for the Google Pixel 3. The urban data campaign took place in Toulouse. 2 vehicles were used where smartphones were placed on the roof of each car, as shown by this diagram. Also, high-quality GNSS receivers were installed in each car for reference purposes. Here we are looking at the data collection campaign that took place in Toulouse. During this campaign, the 2 cars were following each other in the streets of Toulouse. The trajectory is displayed on the picture on the left. During the itinerary, multiple collaborative scenarios represented by the letter has been made. The picture on the right represents the rooftop configuration for our smartphones. We will start our analysis by studying signals tracked by our devices. It appears that in deep urban area, 30 signals were tracked on average on all our tested smartphones. This can be explained by the fact that smartphone chipsets track signals with very low C/N0 compared to the norm, adding to the fact that we now have multi-frequency and multi-constellation receivers. The graph on the left represents the distribution of tracked signals by frequency and constellation. We can see a clear difference between smartphones, brands, and model. The acquisition rate of the L5 frequency seems to be higher for the Galileo constellation, reaching, for some phones, up to 91% of the time. This meaning that for each E1 Galileo signal received, we receive the E5 signal from the same satellite. In this slide, we will take a look at the histogram of track signal in function of their constellation. As stated before, signals are tracked at very low C/N0. When we look at the graph for the GPS signals, we can see that we even have signals tracked for C/N0 lower than 10 dBs. On both figures, we can also see that the C/N0 power level is higher for L5 signals than for L1. A comparison has been made between the error levels found during our data campaign in an urban environment and our estimation made in nominal conditions. On the right, we can see the estimated DLL jitter for the Xiaomi Mi 8. And on the left, we see the standard deviation of the CMC for Galileo satellite recorded by a Xiaomi Mi 8. In both cases, we can see that the error levels are identical and very similar. We can therefore confirm that our estimation method for characterizing smartphone is validated. In order to conclude our smartphone analysis, we drew the most important point for us for the nominal and urban smartphone analysis. So the first one is that Android's phase measurements are unreliable and sometimes are not even retrievable by the smartphone. There is also numerous cycle slip occurrences, and Android flag mechanisms are incompatible with collaborative positioning. Why? because of the inconsistency of multipath detection and the high false alarm rate and occurrences of the cycle slip flags. Then we can also note that the FLP algorithm is mostly responsible for the final positioning performance of the smartphone. Other than that, we saw that there was a great signal availability even in deep urban canyons. And the quality of the recorded GNSS data is also a plus. So overall, what we can say from this study is that the smartphone GNSS data can be modeled and can be used for collaborative positioning. And now let's dive into the collaborative techniques. So first of all, we need to define a collaborative positioning techniques. In order to do so, we will define of how it works and how can it be translated into the smartphone domain and how can we use it in the smartphone domain. So first of all, here we need to define the network architecture. So we have the choice between, on the left, a peer-to-peer network where the users exchange information between every users of the network, or a more centralized infrastructure where all the data goes through a special infrastructure before being emitted to the whole network. In our case, for the smartphone, we would like to have a sum-up structures, which is leaning more toward the peer-to-peer, but where the information can also be centralized and or enhanced by a global server where it can be stored and then redistributed inside the network. The second point is the nature of the data that is exchanged within our network. So here we will make the distinguish between the GNSS only and the hybrid techniques. So in the case of smartphone, again, we will say that we will use hybrid data to be shared within the network because the smartphone today can record many types of data. Then the final one is the implementation method. So here we are looking at where do we apply our collaborative positioning algorithm. In the smartphone domain, in our case, we will have to apply it after the signal processing blocks, just before doing the PVT computation. Our review of smartphone collaborative technique finishes by setting assumption, a goal, and characteristic for the implementation of our smartphone algorithm. The main assumption made here is that the communication link ensures the integrity of exchange data packets and prevents data packet losses. We set as the main goal of our network to be established based on simple assumption, taking advantages of smartphone capabilities and volumes. This golden rule translates into characteristics displayed below. We want to implement a low-cost network without the use of a third-party component. It has to be scalable to the size of a city, and it has to be accessible in a reasonable, easy fashion for multiple smartphone users. By doing so, we expect our method to improve positioning performances by improving at least one performance criteria. Our study also led us to multiple cooperative techniques. However, some of those techniques could not be translated into the smartphone domain. For example, radar ranging and laser ranging cannot be applied since we do not want any third-party component to be involved in our network outside smartphone hardware. 3D city models implies that the network would be usable for only specific areas and specific cities. The same conclusion can be made for 5G location and as well for using smartphone cameras. In the case of Bluetooth and Wi-Fi, only, they can be considered as signal of opportunities. However, using only them as a positioning technique cannot be applied in our case. Those techniques are preferred for indoor positioning. The ranging capabilities of Bluetooth and Wi-Fi are a blocking factor for urban environment. Now that we have our baseline for the implementation of our collaborative network, we will try to do test setups. In order to do so, we are using one of the collaborative scenarios that I presented to you earlier. In this case, we will use scenario C. In this scenario, we put one of the car on the top floor of a building where there was a parking area. This car has been designated as a user in very good condition and in open sky environment. The second user was orbiting around this building in a more deep urban canyon. Now, the good point about this scenario is that it represents a real life event that could happen, and the GNSS condition differs from the user 1 and 2. So here is the aerial map of our test setup for the scenario C. So here, as you can see, we have the green dots, which represent our static and open sky user. This user is going to be the one aiding the other one, which is in a more urban environment. Now, the second user, which in this case I called user A, is circulating around the block around this parking place. As we can see, there is a lot of error compared to the reference trajectory that was taken by our span receiver. Our tests are based on a dual PVT algorithm solution. The two positioning solutions are estimated simultaneously. Therefore, we will be able to implement a collaborative scenario in this case. Now, for reference purposes, we did a positioning error compared to our span trajectory. As you can see, for the smartphone that was in a difficult situation, there is a 40 meters error without any cooperation. Now, this will be the starting point for all the testing we will be making in the future. We are now arriving to the end, and let me show you the conclusions of this presentation. Finally, to conclude, our deep Android raw data measurement analysis allowed us to confirm that smartphone positioning performance differs from phone to phone and from chipset model. The urban data campaign showed us that smartphone capabilities are quite outstanding for such very low-cost receiver, even with their well-known limitation of smartphone hardware. We then demonstrated that our assessment methodology for smartphone characterization is viable. We recommend to estimate the four main errors budget parameters, which are the DLL, PLL, Doppler jitter, and the clock drift. For urban cases, the analysis of recorded signals allowed us to better understand the black box processes inside a GNSS embedded receiver. Additional Android data, such as multipath and cycle slip flag detection, should be regularly monitored by the scientific community since they might improve considerably in the future. Overall, our collaboration techniques, state-of-the-art research, enabled us to create the roots for our collaborative smartphone network. Those are the paper references that I used for this presentation. Thank you very much for following this presentation with me today. I hope that you enjoyed my research work. This study and my PhD is financed by CNES, TESA, and Thales Alenia Space. Feel free to ask me questions about my presentation and my work in the comment section below. I'm looking forward to see you soon. Stay safe.